Welcome back to this deep learning playlist. Please consider subscribing to the channel if you are new here and consider watching all the tutorials in sequence to have a better grip on the subject. So in the previous lecture, we tried to gain the fundamental understanding around a perceptron. We have learned that a perceptron works really well in terms of a linear data. And we also learned that it fails to perform well in terms of a non-linear data like this one. And within this lecture, we will explore the method of combining the efficiency of multiple perceptrons to solve for a non-linear data as well. So in this video, we are talking about multi-layer perceptron. In simple words, we are going to talk around the idea of multiple perceptrons working together in order to solve a non-linear problem like this one. So we are already aware that the way a perceptron works, it can solve a problem like this or this. So depending upon the value of these weights, a perceptron can draw a straight line like this or this. But you can see in both the cases, performance is not that good. In fact, we are looking for a non-linear solution like this one. And achieving this kind of solution can be possible by combining two perceptrons or performance of two perceptrons. One of them that gives a straight line like this one and other one that gives a straight line like this one. And we are going to learn about how it is possible to combine these two performances in order to come up with this non-linear solution. In fact, you can also combine more than two perceptrons like over here I am doing. And each of these perceptrons, since they have different values for their respective weights, they are providing a different straight line in each case. And combining the performance of multiple perceptrons, you can even achieve a further complex model like this one. So let's move ahead and explore first that how does a multiple layer perceptron model looks like. So this is a very simple model where we are using two perceptrons and combining their performances in order to achieve a non-linear model. So you can see x1 and x2 are the inputs from the feature values. P1 and P2 are two different perceptrons that we are using, and combining their performance in the third perceptron, which is in the next layer, and then the final equation will be sent out to the activation function to produce the output. So let's move ahead and explore this simple model in more details. So x and y are two different features that we are using here to calculate the output. This feature x will be multiplied by this weight a1 and then it will be sent out to the first perceptron. Similarly, this feature x will be multiplied with this weight a2 and it will be sent out to the second perceptron. On the other hand, this input y will be multiplied by this weight b1 and it will be sent out to the first perceptron. And again, the same input will be multiplied by this weight b2 and will be sent out to this second perceptron. So the equation in the first perceptron will look something like this. We will call it z1 and it will be x multiplied by a1, which is this and this, plus y multiplied by b1, which is this and this, plus c, which is a bias term. Again, the equation on the second perceptron, we are calling it here z2, and the equation looks like this: x a2, which is this feature and this weight, plus y b2, which is this feature and this weight, plus c2, which is the bias term in the second perceptron. And since now we understand how z1 and z2, the equations on first perceptron and second perceptron respectively, is being calculated, this entire equation, which means the value of z1, and this entire equation, which means the value of z2, will now become the inputs for the third perceptron, which is p3. So z1 will be multiplied by this weight a3 over here, and z2 will be multiplied by this weight b3 over here, and C3 will be the bias for the third perceptron. And since this was a linear model and this was a linear model, combining the linear performance from both the perceptrons over here in this step is now becoming non-linear. So this entire equation is actually non-linear that has been obtained from these two linear equations. And it is the exact idea that I was talking about previously over here when I was saying that we can combine the performance of multiple perceptrons. Each will have a linear solution and we can combine them in such a way that we will achieve a non-linear solution which is required for our particular use case. So this nonlinear equation will be sent out finally to this activation function that we can choose depending upon the problem that we are solving. And by the way, don't worry, we have not explored the topic of activation function in detail so far. So it is absolutely okay if the term activation function is not making much sense to you. We are going to have a dedicated lecture on this topic. For the time being, you can simply assume that activation function is nothing but a formula that will receive this equation and it will interpret it in such a way that the output will help us to make the prediction. And this was a simple explanation for a very simple neural network. Going forward, we will also explore some complex neural networks, but this was the most simple one that you can get started with. And over here, this area will be the input where we are passing the value of the features to the model or to the neural network. This layer is called the input layer, and within this layer, you can have more than two neurons as well. By the way, neurons and perceptrons are the same thing. You can use them vice versa. Moving ahead, this layer is called the hidden layer. Again, within this layer as well, you can have multiple perceptrons or neurons, and this is the output layer. So if you are solving a regression problem or a classification problem with only two classes, in that case, you will use only one neuron or only one perceptron on this output layer. In case you are solving a classification problem where you have more than two classes, let's say you are trying to classify between three classes, which is 1, 2, and 3. Or let's say yes, no, or maybe, or good, bad, or neutral, something like that. Okay. In that case, within this layer, within the output layer, you will have three perceptrons or three neurons. And you will choose an activation function in such a way that if the model is predicting for this class, then it will have the highest probability, let's say 0.8, and others will have lesser probability, let's say 0.1 and 0.1 for this one. And going by this number, you can do the classification between multiple classes. So I hope that you were able to gain a basic understanding around a simple neural network and how we are combining the efficiency of multiple perceptrons in order to achieve a non-linear solution. Let's explore another interesting thing. Let's say that we have two perceptrons, this and this one. Okay, this perceptron is giving you a straight line like this, and this perceptron is giving you a straight line like this one. However, in reality, you are looking for this non-linear solution. Okay, so we need to combine these two solutions in such a way so that we can obtain this non-linear solution. And let's assume that in order to obtain this solution, this straight line or this prediction from the second perceptron has more importance compared to this straight line predicted by this perceptron. In that case, let's say the weights assigned to these two perceptrons are W1 and W2 respectively. So the model will make sure that the value of W2 should be higher than W1 because this particular prediction or straight line is contributing comparatively more in order to achieve this non-linear solution. So again, if we try to understand the same with the help of this simple neural network, it works something like this. That Z1 is a straight line produced by P1 perceptron and Z2 is a straight line predicted by perceptron P2. And the actual non-linear equation that we are trying to achieve over here, Z2 has a greater contribution towards that. In that case, B3, which is a coefficient of Z2, will have a higher value compared to A3, which is a coefficient of Z1. So this was another conceptual thing that I wanted to talk about. Now let's move ahead. So in the previous lecture, we explored about perceptron and we learned that how efficient and well performing it is in terms of solving for a linear data. And it also comes along with a problem of not performing well with a non-linear data. And within this lecture, we have explored that how we can use and combine the power of multiple perceptrons in order to achieve a non-linear solution. You can see this is the first layer where we have 4 perceptrons, which means we are using 4 features in order to predict the outcome. And this neural network has 2 hidden layers. First is this one and second is this one. Both of them have 6 perceptrons respectively. And in the output layer, we have 2 perceptrons. That clearly means that over here we are solving a classification problem that has 2 different classes. And this connection that you can see, it is called the dense connection. Dense because each perceptron within a given layer is connected to all the perceptrons in the following layer with a combination of multiple weights. And this was an overview around neural network. Going ahead, we are going to explore a lot of things around the function and properties of a neural network. So starting from backpropagation, chain rule, gradient descent, issues like vanishing gradient and exploding gradient, and also how do we tackle overfitting in a neural network. Everything we are yet to discuss and discover within this playlist. And over here I have a very interesting slide to show you. With a simple and interesting storytelling, I will try to explain that how a multiple layer perceptron works in order to produce a desired outcome. So let's say we are using a text input and the text is I see a picture of a mouse. So this is the input over here. Okay. Now for a minute, let's not discuss about that. How do we convert these texts into numbers or vectors before passing it into the neural network? We will cover that in a different playlist based on NLP. But for the time being, just assume that the input coming in is a text input. And this is the text that we have over here. And in the first layer, we have three perceptrons, 1, 2, and 3. In the first perceptron, weights are adjusted in such a way that if it receives the data of a mouse, it will interpret that as a normal mouse. In the second perceptron, weights are adjusted in such a way that if it receives the input as a mouse, it interprets that as a device mouse, as a computing peripheral. Similarly, in the third perceptron, weights are set in such a way that if it receives the input as a mouse, this will interpret the information as Mickey Mouse character. So if our input is I see a picture of a mouse, then it becomes very difficult to say that which mouse we are talking about. And therefore, let's say if the weights over here are W1, W2 and W3, all of them will have equal say. So 0.33, 0.33 and 0.33. But now let's assume that I am adding more data to this text. So I will say I see a picture of a mouse and he is eating cheese. And after this change in the input, the weights assigned here will be changed. Because of course this computing peripheral will not eat cheese, so the weights over here will be changed. So this will be changed to, let's say, 0.1 and this will be changed to, let's say, 0.2 because there is some possibility of Mickey Mouse eating the cheese. However, this will have the maximum say this time. So this will be changed to 0.7 and this is the point that I'm trying to make. Each of these perceptrons will be assigned different kind of weights, which means the way it interprets the data and gains the understanding out of it will be different for each of the perceptron. And after taking all of their inputs, when we try to draw a conclusion and when we try to come up with the output, which is, let's say, y hat, then we also calculate the loss, which is the real value minus predicted value. And if this loss is too big, in that case, the algorithm will go back and will adjust these weights accordingly, so that we can reduce this loss. However, this lecture is not for backpropagation, so I will not emphasize much on that, but you get the idea. Let's try to make more changes to this text. Okay, so I will erase this and let's say this time our input is I see a picture of a mouse and next I will say it is broken. So obviously this value for this particular mouse will be reduced because it is not making much sense this mouse being broken. The value for this particular perceptron as well will be changed. And since this mouse being a computing peripheral, there is a high chances that you might see it broken, right? So this will have the maximum weight and this will have the maximum say in the final output as well. So I know that within this particular slide, I have used a very silly example, but trust me, it helped me a lot initially when I was trying to understand the concept of multi-layer perceptron and how their weights changes according to the output and the calculated loss. So in order to reduce the loss, these weights will be changed accordingly. And by the way, achieving the perfect value for these weights is actually called training of your model. This is the exact thing which is happening during the convergence. By the way, we will also explore that when we will cover the gradient descent topic for deep learning. So do not worry about that. For this particular lecture, I hope that you found it useful and you were able to gain a decent understanding around a simple neural network. Also, let me know your thoughts below if you liked this particular demonstration. If yes, then I will try to use this kind of demonstrations going ahead with the upcoming tutorials. And do not forget to drop a like below before you close this video. I am working really hard to create these tutorials and the number of likes on this given video will help me to push my tutorial videos to more number of people. in order to help the channel grow. In the upcoming lecture, we will gain an in-depth understanding around backpropagation in a neural network. So that will be a really important video. So please do not miss that. It will work as a foundation for your knowledge on deep learning and will help you a lot in interviews as well. Thank you very much for watching till the end. You have a nice day ahead.